A few hundred years ago, Isaac Newton demonstrated how you can use a glass prism to split sunlight into the colors of the rainbow. So let's say that's the sun. Okay, that's the sun. And let's imagine that Newton, let's imagine that Newton covered up his window. Right, he covered up his window, but make a little hole in the window just to allow some a small narrow ray of sunlight to come through. And he put a prism in the way of the sunlight, glass prism. So as the sunlight comes through the little hole in his window and goes through the prism, it splits up into the colors of the rainbow. So for example, it splits up into red, splits up into orange, bands a little bit more, the yellow light bands a little bit more, the green light bands a little bit more, the blue light bands a bit more, indigo, I think that's indigo, and violet. So each of the color band a little bit differently, and he ended up with this spectrum, this rainbow, the full set of colors from the rainbow. Okay, so let's imagine that he put a screen or a piece of paper there, and this is what he observed on that piece of paper. And maybe a white piece of paper down here. Okay, so this is this. Right, now this and his room is probably dark, so if you shut off the hole in the window, then it'll just be dark. Okay, so around the paper is dark. It's just this part where the colored rainbow falls on the paper that he sees the light. Now we are actually quite familiar today with rainbow and colors of the rainbow. Now there is something about this rainbow that we hardly ever give a thought to, but which is going to be very important in the physics that I'm going to talk about in this and the coming videos. And this particular feature about this rainbow, this spectrum, this particular feature, which is very unusual, is that it is continuous. Well, very unusual in the sense that in the context of what I'm going to talk about, but it's very common, of course, in everyday life. So it is this feature that I want to emphasize for a start, that the white light spectrum from the sun is, or at least it looks like a continuous, band of colors. You don't see any break in between. Okay, and that looks perfectly normal to us because we're so used to it. But wait till you look at the next example. Okay, so in the next example, here's what I'm going to do. Let's imagine this time that I have I instead of using the sun, I'm going to use a fire Okay, so let's have a fire. Now I'm going to use a Bunsen burner. So this is a little gas burner. So just let's say there's some gas coming through here, and we light this up with a match, and we get a fire. Okay, so that's my fire here, and it sort of gets very hot around here. Now, but I'm not so interested in the color of the fire right now. Imagine that. Okay, let's just imagine that I take say a long metal spoon, a long or spatula as they might call it in chemistry. So just a little spoon, and I put some common salt on the spoon. You know, the salt that we use for our food, that you sprinkle on your chips or rice, or whatever you like to eat. Okay, so that's salt. That's just common salt. It's sodium chloride, something we can just buy in the shops. Okay, now the moment you stick this lump of salt into the very hot flame, something very spectacular happens. And the salt is just some white powder that we see every day. But the moment you put it in this very hot flame, the whole flame turns orange. That doesn't look very good. Right, the whole flame turns orange, so it starts giving out orange light. And it is this orange light that I want to see the spectrum of. So I'm going to set up this part in a similar way with one important difference. I'm going to have a screen there. Doesn't have to be a window this time, because we're not taking light from the sun. So it might be just a piece of paper or piece of metal with a hole down here that allows some light from this burning or this heated lump of salt, some light from there to come through. But this time I am not going to use a prism. Instead, I would use a diffraction grating. Now, in my much earlier videos on diffraction grating, I've explained how diffraction grating can band light a lot and produce a spectrum. Right, it can band light and produce a much broader spectrum. Alright, that means, in other words, you can stretch out the spectrum a lot more using a diffraction grating compared to a prism. Now, and that is important for such an experiment, because we want something that can really stretch out the spectrum so that we can see each individual colors and see the spacing between them clearly, and in particular, using the diffraction grating, we also know how to measure the wavelength, and that's going to be important. Right, let me just write down the formula for the wavelength. D sine theta equals to n lambda. So just by measuring the band angle as the ray of light goes through the diffraction grating, the band angle theta, we can calculate the wavelength. Okay, so lots of advantages of using a diffraction grating. So that's what we would use from now on. And in fact, that was in use from maybe around about the 19th century onwards. Okay, so with this diffraction rating, this yellow, this orange light from the heated sodium will go through it, and there would be fringes. There will be one that goes straight, that's the central fringe. There would be those that rays that go up and go down to the first order fringe. As it turns out, in the case of sodium chloride, the light ray is pretty pure orange, but there are actually two slightly different wavelengths of orange that's produced by the sodium chloride, as I will draw in a moment. So actually there are two rays very close together going to the first order spectrum. Okay, so if we imagine that this falls on a piece of paper, okay, just put a piece of paper here to observe the spectrum. What would it look like? It would look like, draw the piece of paper here. Now this time, you won't see a continuous spectrum, you won't see any rainbow color. What you would see is something very different. You would see this. You would see two orange lines very close together. Okay, I'm drawing this very well. One line. Two orange lines very close together on the spectrum. So no continuous spectrum, no colors at all. Now, it's not surprising if you have seen the color of sodium chloride. It's not so surprising that you would not see all the colors of the rainbow, that it would kind of look orange. But what was surprising was that the fact that that the spectrum shows as just two very sharp lines, right? It's like two lines that you would draw with your pencil. Two very sharp lines, and doesn't look anything like the sun's spectrum, like the rainbow colors where you have a spread, right? There isn't even any spread of color or any spread of this spectrum. Just two very sharp lines. And that is what is very unusual about it. And there is a name for this kind of spectrum. It's called a line spectrum, as opposed to the continuous spectrum of sunlight. So this is called a line spectrum, and in fact it is observed for many other compounds and elements. Okay, and so just to give an idea of what comes later, let me write down the wavelength of this. So the wavelength in nanometer, as I said, is something that you could easily measure, well, to some kind of easily once you get used to it, by measuring this angle and then using this formula with n equals to 1 to calculate the wavelength. The D is usually known, given by the manufacturer when you buy the diffraction rating. So lambda can be calculated, and from measurements that people have made, the wavelength of those two lines Okay, for this one is 589.0 nanometer. For this one is 588.6 nanometer. So I'm writing these numbers down because it will be relevant to something that I will talk about afterwards. Right. Now let me just have a quick look before I finish this part of this particular video at another example. Right, so this time instead of burning common salt in a fire, I'm going to do something slightly different. Now, this is a glass tube. Let's say this is a glass tube with hydrogen gas inside. Okay, and suppose that is enclosed, but it's airtight. Okay, with hydrogen gas inside at a low pressure, so that it is possible to have, if we put in two metal plates inside and connect to a high voltage, maybe a few hundred or 1,000 volts, for an electric current to jump across to jump through the vacuum or through the hydrogen gas inside. Current of electrons going through. Now, when this kind of a tube is called a discharge tube. Discharge as an electric discharge. When this electric current goes through the hydrogen gas, light will be produced. The hydrogen gas will start producing light. Okay, so you start glowing. But the color is quite mixed. You'll see why in a moment. Maybe a little bit of reddish and bluish tints mixed together. Okay, so once again we're going to pass this through a little hole in maybe a glass a metal sheet. Okay, so we have this light coming through. This light's coming through. And once again, we're going to use a grating so we can measure the wavelengths accurately. And there would be a few colors coming through. Right, there would be a red color. Now this time I'm just going to draw the first order fringe spectrum on the lower side. There would be this color. There would be another color, and there would be this color. So you would actually see 4 colors if you allow them to fall on a piece of white paper. Okay, so let me draw this spectrum. So magnified view of this. Now if you look at this piece of paper, if you actually set up this experiment, look at this piece of paper, you will see a very sharp red line. You'll see a line. I think we call this color cyan, sort of in between green and blue. You'll see a blue line. You will see a kind of a slightly purplish line. Maybe this is called indigo. Not too sure about the name of the color. But anyway, these are almost exactly the kind of colors that you would see when you get this light coming out from hydrogen and going through a grating to produce spectrum. Right. Now once again, let me just write out quickly the values of the wavelengths. And in the case of hydrogen, as we will see, the wavelengths of these lights turns out to be very important for what comes next when we talk about the hydrogen atom. That wavelength is 656.3. That one is 486.1. That one is 410.2. And that one is 434.0.